A 4000 amp service voltage pressure switch tripped, and resetting it without proper diagnosis was not recommended. The electrical service exhibited an unusual configuration with both 208/120 volts and 480/277 volts power available. A 1250 kV amps transformer connected to the 208/120 volt service lacked overcurrent protection on the line side. A 400 amp fused safety switch that fed a 400 amp main distribution panel had shorted A and B phase conductors because of inadequate conduit capacity and thermal stress. The initial call involved a ground fault trip, however. No obvious cause was found during the initial investigation. The ground fault relay was set to trip at 700 amps with a 15-second delay. A subsequent call revealed that A and B phase conductors and a fused safety switch were shorted. 400 amp conductors were bundled within a 2-inch electrical metallic tubing conduit. The conduit size resulted in inadequate ventilation and an excessive buildup of heat. The melting of the insulation caused a short circuit, which then tripped the main line switch. Utility current transformers were lifted from an energized current transformer cabinet, which presents a safety hazard. The absence of overcurrent protection on the line side of the transformer represents a potential fire hazard. Firstly, inform the utility about the energized current transformer cabinet and recommend that they place signage to highlight the potential hazard. Secondly, provide appropriate overcurrent protection for the primary side of the transformer. Thirdly, resolve the issue of inadequate conduit capacity and excessive heat buildup in the fused safety switch by using a larger conduit or by installing separate conduits for each phase conductor. Fourthly, investigate the underlying cause of the ground fault trip. Consider factors such as insulation damage, ground loop issues, or harmonics. In a more detailed analysis, it is crucial to understand the implications of the shorted conductors and the ground fault issue. The short circuit within the 400 amp fused safety switch is a serious safety concern. The inadequate conduit fill, with multiple 400 amp conductors bundled together, restricts airflow and leads to thermal overload. The heat generated by the current flow in these conductors cannot dissipate effectively, causing the insulation to break down and eventually melt. This melting insulation creates a conductive path between the A and B phases, resulting in a short circuit. The short circuit draws a massive amount of current, far exceeding the 400 amp fuse rating, causing the fuse to blow and the main line switch to trip. The ground fault issue is more complex and requires careful investigation. A ground fault occurs when current flows from a phase conductor to ground through an unintended path. This can happen due to damaged insulation, moisture, or faulty equipment. The ground fault relay is designed to detect this current imbalance and trip the circuit breaker to prevent electrical shock and equipment damage. The fact that the ground fault relay tripped without any immediately apparent cause suggests an intermittent or hidden fault. It is essential to thoroughly inspect all wiring, connections, and equipment for any signs of damage or degradation. Ground loops can also cause ground fault trips. A ground loop occurs when there are multiple paths to ground, creating a circulating current. This current can interfere with the ground fault relay and cause it to trip unnecessarily. Harmonics, which are distortions in the sinusoidal waveform of the electrical current, can also trigger ground fault relays. Harmonics are typically generated by nonlinear loads such as variable frequency drives and electronic equipment. To address the issues, consider the following. For the shorted conductors, firstly, replace the damaged conductors with new ones of the correct size and insulation rating. Secondly, install a larger conduit or separate conduits for each phase conductor to ensure adequate ventilation. The National Electrical Code, Section 310.15 details ampacity correction factors and conduit fill requirements. Thirdly, ensure that all connections are tight and properly insulated. For the ground fault issue, firstly, perform a thorough insulation resistance test on all conductors to identify any insulation damage. Secondly, check for ground loops and eliminate any unnecessary grounding paths. Thirdly, analyze the harmonic content of the electrical system and install harmonic filters if necessary. For the transformer, firstly, install overcurrent protection on the primary side of the transformer. The overcurrent protection device, such as a circuit breaker or fuses, should be sized according to the transformer's kVA rating and the primary voltage. NEC Section 450.3 provides guidance on transformer overcurrent protection. Secondly, ensure that the transformer is properly grounded and that all connections are tight. For the utility current transformers, inform the utility about the safety hazard and request that they install signage to warn personnel about the energized equipment. Consider installing a barrier or enclosure around the current transformer cabinet to prevent accidental contact. Additional safety measures should include regular inspections of the electrical system to identify and address any potential hazards. Training personnel on electrical safety procedures and the proper use of personal protective equipment is also crucial. It is also important to document all findings, recommendations, and corrective actions taken. This documentation will be valuable for future troubleshooting and maintenance. The unusual service configuration with both 208/120 volts and 480/277 volts power may require additional coordination and communication with the utility. Ensure that the utility is aware of the transformer installation and that they have the necessary information to safely operate and maintain the electrical system. A comprehensive approach that addresses both the immediate safety concerns and the underlying causes of the electrical problems is necessary. By implementing these recommendations, the customer can ensure the safety and reliability of their electrical system and prevent future incidents. When dealing with a 4000 amp service, safety is paramount. Always energize the equipment before performing any work and use appropriate personal protective equipment, including gloves, eye protection, and arc flash protection. If you are not qualified to work on electrical equipment, hire a licensed electrician. The complexity of a 4000 amp service requires specialized knowledge and experience. A qualified electrician will be able to properly diagnose and repair any electrical problems and ensure that the system is safe and reliable. Furthermore, the presence of a 1250 kV amps transformer without line-side overcurrent protection is a significant code violation and safety hazard. The National Electrical Code requires that transformers be protected against overcurrent to prevent damage to the transformer itself and to protect the electrical system from potential faults. The overcurrent protection device should be sized according to the transformer's kVA rating and the primary voltage. In this case, the primary voltage is 208 volts and the kVA rating is 1250 kV amps. The primary current can be calculated as follows. Primary current equals kVA asterisk 1000/volts asterisk square root 3. Primary current equals 1250 asterisk 1000/208 asterisk square root 3. Primary current equals 3470 amps. Therefore, the overcurrent protection device should be sized to protect the transformer against a primary current of 3470 amps. However, the National Electrical Code also limits the size of the overcurrent protection device to a certain percentage of the transformer's rated primary current. This percentage varies depending on the type of overcurrent protection device and the transformer's impedance. According to NEC Section 450.3, the overcurrent protection device for a transformer with an impedance of 6% or less should be sized to no more than 125% of the transformer's rated primary current. In this case, the transformer's rated primary current is 3470 amps, so the overcurrent protection device should be sized at no more than 4337.5 amps. However, the overcurrent protection device cannot be larger than the next standard size above the calculated value. Therefore, the overcurrent protection device should be sized at 4000 amps. It is important to note that the overcurrent protection device should be installed on the primary side of the transformer, as close as possible to the transformer terminals. This will provide the best protection against faults and overloads. In addition to overcurrent protection, the transformer should also be protected against ground faults. A ground fault occurs when current flows from a phase conductor to ground through an unintended path. This can happen due to damaged insulation, moisture, or faulty equipment. A ground fault protection device, such as a ground fault relay or a ground fault circuit interrupter, is designed to detect this current imbalance and trip the circuit breaker to prevent electrical shock and equipment damage. The ground fault protection device should be sized according to the transformer's kVA rating and the primary voltage. In this case, the primary voltage is 208 volts, and the kVA rating is 1250 kV. The ground fault protection device should be set to trip at a current level that is low enough to protect against ground faults but high enough to avoid nuisance tripping. A typical ground fault protection setting is 30 mA. The ground fault protection device should be installed on the secondary side of the transformer as close as possible to the transformer terminals. This will provide the best protection against ground faults. By installing proper overcurrent and ground fault protection for the transformer, the customer can ensure the safety and reliability of their electrical system and prevent potential fire hazards. The issue with the 400 amp fused safety switch is another significant safety concern. The fact that the A and B phase conductors were melted together indicates that the conductors were subjected to excessive heat. This heat was likely caused by a combination of factors, including excessive current flow, inadequate conduit fill, and poor ventilation. Excessive current flow can be caused by an overload or a short circuit. An overload occurs when the current flowing through the conductors exceeds their ampacity rating. A short circuit occurs when there is a direct connection between two conductors of different potential. In either case, the excessive current flow will generate heat, which can damage the conductors and their insulation. Inadequate conduit fill occurs when the number of conductors in a conduit exceeds the maximum allowed by the National Electrical Code. When too many conductors are packed into a conduit, it restricts airflow and prevents heat from dissipating. This can lead to a buildup of heat, which can damage the conductors and their insulation. Poor ventilation can also contribute to the buildup of heat. If the conduit is located in a confined space with poor ventilation, the heat generated by the conductors will not be able to dissipate effectively. This can lead to a buildup of heat, which can damage the conductors and their insulation. To address the issue with the 400 amp fuse safety switch, the following steps should be taken. Firstly, determine the cause of the excessive current flow. If the excessive current flow was caused by an overload, the load should be reduced or the conductors should be upgraded to a larger size. If the excessive current flow was caused by a short circuit, the short circuit should be located and repaired. Secondly, reduce the conduit fill to the maximum allowed by the National Electrical Code. This can be done by removing some of the conductors from the conduit or by installing a larger conduit. Thirdly, improve the ventilation around the conduit. This can be done by opening up the space around the conduit or by installing a fan to circulate air. Fourthly, replace the damaged conductors with new conductors of the correct size and insulation rating. It is important to use conductors that are rated for the temperature at which they will be operating. The National Electrical Code specifies the allowable ampacities of conductors at different temperatures. By taking these steps, the customer can ensure the safety and reliability of the 400 amp fuse safety switch and prevent future problems. The energized utility current transformer cabinet is a serious safety hazard that should be addressed immediately. Current transformers are used to measure the current flowing through a conductor. They are typically installed on the primary side of a transformer or on a feeder circuit. Current transformers produce a very high voltage when they are open-circuited. This voltage can be lethal. Therefore, it is essential to never open-circuit a current transformer while it is energized. The utility should have procedures in place to ensure that current transformers are de-energized before they are opened. These procedures should include isolating the current transformer from the electrical system and grounding the current transformer terminals. The utility should also train its personnel on the proper procedures for working with current transformers. In addition to the utility's procedures, the customer should also take steps to protect their personnel from the hazards of energized current transformers. These steps should include installing barriers or enclosures around the current transformer cabinets and posting warning signs to alert personnel to the potential hazards. The customer should also train their personnel on the dangers of energized current transformers and the proper procedures for working around them. By taking these steps, both the utility and the customer can help to prevent accidents and injuries related to energized current transformers. The ground fault protection system that tripped is set at 700 amps with a 15-second delay. The settings should be appropriate for the size and type of electrical system being protected. The purpose of ground fault protection is to detect and interrupt ground faults, which can cause electrical shock, fire, and equipment damage. A ground fault occurs when current flows from a phase conductor to ground through an unintended path. This can happen due to damaged insulation, moisture, or faulty equipment. The ground fault protection system typically consists of a ground fault sensor, a ground fault relay, and a circuit breaker. The ground fault sensor monitors the current flowing in the grounding conductor. If the current exceeds a certain threshold, the ground fault sensor signals the ground fault relay. The ground fault relay then trips the circuit breaker, which interrupts the flow of current to the faulted circuit. The ground fault protection system should be tested periodically to ensure that it is functioning properly. The testing should be performed by a qualified electrician. The electrician will use a ground fault tester to simulate a ground fault and verify that the ground fault protection system trips the circuit breaker. The electrician will also inspect the ground fault protection system components for any signs of damage or wear. If the ground fault protection system is not functioning properly, it should be repaired or replaced. The cost of repairing or replacing a ground fault protection system is typically much less than the cost of the damage that can be caused by a ground fault. Therefore, it is important to maintain the ground fault protection system in good working order. The recommendation to install signage to warn personnel about the energized utility current transformer cabinet is an important safety measure. The signage should be clear, concise, and easy to understand. The signage should also be placed in a location where it is readily visible to personnel who may be working around the current transformer cabinet. The signage should include the following information. Firstly, a warning that the current transformer cabinet contains energized equipment. Secondly, a warning that the equipment can be lethal. Thirdly, instructions on how to avoid contact with the equipment. The signage should also include the name and phone number of the person to contact in case of an emergency. In addition to signage, it is also important to provide training to personnel who may be working around the current transformer cabinet. The training should cover the hazards of energized equipment, the proper procedures for working around energized equipment, and the location of the emergency contact information. By providing signage and training, the customer can help to protect their personnel from the hazards of energized utility current transformer cabinets. The recommendation to provide proper overcurrent protection for the transformer's primary side is a critical safety measure. Overcurrent protection is designed to protect the transformer from damage caused by overloads and short circuits. Overloads occur when the current flowing through the transformer exceeds its rated capacity. Short circuits occur when there is a direct connection between two conductors of different potential. In either case, the excessive current flow can generate heat, which can damage the transformer's insulation and windings. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds a certain threshold. The overcurrent protection device should be sized to protect the transformer from damage without causing nuisance tripping. Nuisance tripping occurs when the overcurrent protection device trips unnecessarily due to transient current surges or other non-fault conditions. The overcurrent protection device should be selected based on the transformer's kVA rating, primary voltage, and impedance. The National Electrical Code provides guidance on selecting the appropriate overcurrent protection device for transformers. The overcurrent protection device should be installed on the primary side of the transformer as close as possible to the transformer terminals. This will provide the best protection against faults and overloads. In addition to overcurrent protection, the transformer should also be protected against ground faults. A ground fault occurs when current flows from a phase conductor to ground through an unintended path. This can happen due to damaged insulation, moisture, or faulty equipment. Ground fault protection devices, such as ground fault relays and ground fault circuit interrupters, are designed to detect and interrupt ground faults. The ground fault protection device should be sized to protect the transformer from damage without causing nuisance tripping. The ground fault protection device should be installed on the secondary side of the transformer, as close as possible to the transformer terminals. This will provide the best protection against ground faults. By providing proper overcurrent and ground fault protection, the customer can help to protect their transformer from damage and ensure the safety of their electrical system. The recommendation to address the inadequate conduit capacity and excessive heat buildup in the fuse safety switch is a crucial safety measure. Inadequate conduit capacity can lead to overheating of the conductors, which can damage the insulation and create a fire hazard. Excessive heat buildup can also damage the fuse safety switch itself, which can lead to equipment failure and electrical shock hazards. To address the inadequate conduit capacity, the customer should either install a larger conduit or install separate conduits for each phase conductor. The National Electrical Code provides guidance on determining the appropriate conduit size for a given number of conductors. The conduit size should be large enough to accommodate the conductors without overcrowding them. The conduit should also be made of a material that is suitable for the environment in which it is installed. To address the excessive heat buildup, the customer should ensure that the conduit is properly ventilated. The conduit should be located in an area where there is adequate airflow. The conduit should also be shielded from direct sunlight and other sources of heat. In addition to addressing the conduit capacity and heat buildup, the customer should also inspect the fuse safety switch for any signs of damage or wear. If the fuse safety switch is damaged, it should be replaced immediately. The customer should also ensure that the fuses in the fuse safety switch are properly sized and installed. The fuses should be sized to protect the conductors and equipment that are connected to the fuse safety switch. By addressing the inadequate conduit capacity, excessive heat buildup, and condition of the fuse safety switch, the customer can help to prevent fires, electrical shock hazards, and equipment failures. The recommendation to investigate the root cause of the ground fault trip, considering factors such as insulation damage, ground loop issues, or harmonics, is an important step in preventing future ground fault trips. Ground fault trips can be caused by a variety of factors, including insulation damage, ground loop issues, and harmonics. Insulation damage can occur due to aging, wear and tear, or exposure to harsh environments. When insulation is damaged, it can allow current to leak to ground, which can trigger a ground fault trip. Ground loop issues occur when there are multiple paths to ground. This can create a circulating current that can interfere with the ground fault protection system and cause it to trip unnecessarily. Harmonics are distortions in the sinusoidal waveform of the electrical current. Harmonics can be caused by nonlinear loads such as electronic equipment and variable frequency drives. Harmonics can also interfere with the ground fault protection system and cause it to trip unnecessarily. To investigate the root cause of a ground fault trip, the customer should perform a thorough inspection of the electrical system. The inspection should include the following steps. Firstly, inspect all conductors for signs of insulation damage. Secondly, check for ground loop issues by verifying that there is only one path to ground. Thirdly, analyze the harmonic content of the electrical current using a harmonic analyzer. Once the root cause of the ground fault trip has been identified, the customer can take steps to correct the problem. If the ground fault trip was caused by insulation damage, the damaged conductors should be replaced. If the ground fault trip was caused by ground loop issues, the ground loop should be eliminated. If the ground fault trip was caused by harmonics, harmonic filters should be installed. By investigating the root cause of ground fault trips and taking corrective action, the customer can help to prevent future ground fault trips and ensure the safety of their electrical system.